Right now, as you're watching this, you are not touching anything. Not the chair under you, not the floor under your feet, not the clothes resting on your skin. You feel like you are. You're absolutely convinced you are. Your nervous system is sending you a constant stream of yes, 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 I'm touching this. But the truth is, you are not. You never have. Not once. Not in your entire life. And neither has anyone else. Now that sounds like I've lost my mind. So let me say this carefully. This isn't mysticism. It isn't philosophy. It isn't some game with words where we sneak a definition through the back door and then pretend we've proven something. This is physics. Hard, boring, reliable physics. The kind that lets you build transistors and MRI machines and lasers and satellites. The kind that works whether you believe it or not. And by the end of this talk, you'll see exactly why the universe is arranged so that touching is not what you think it is. And I suspect you'll find it not depressing, but delightful. Here's the even stranger part. Not only have you never touched anything, you have never even come close. The distance between you and everything you've ever touched is roughly a 10 millionth of a centimeter. That's an absurdly small number on human scales, but at the scale of atoms it's huge. It's not a hairline crack, it's a canyon. It's a gap that is never once closed, and yet you feel contact, you feel resistance, you feel texture, you feel pressure, you feel warmth. So what's going on? How do you get the experience of touch if there is no literal touching? That's the puzzle. And the solution takes us on a trip through electromagnetism, quantum mechanics, and the real structure of matter, what solid really means, what surface really means, and what your skin is actually sensing when you think you're in contact with the world. Let's start simple, almost insultingly simple. Put your hand on a table. If there's one nearby, do it. Feel that immediate stop, that sense of, I can't go any farther. Now ask, what's happening? Most people would say something like the atoms in my hand are bumping into the atoms in the table. It sounds obvious. It sounds like common sense. It's also fundamentally wrong. Not a little wrong. Not technically wrong. Wrong in the way that a bad map is wrong. It points you in the opposite direction of the truth. To see why, we have to talk about what an atom actually is. You've probably seen the cartoon atom, a nucleus like a little ball in the center, and electrons orbiting around it like planets around a sun. That picture has historical value. It helped people think. It helped them guess some right things. It's not totally worthless, but for what we're doing today, it plants the wrong idea in your head. It makes atoms feel like tiny, hard objects with surfaces, like miniature marbles. They aren't. An atom does not have a surface in the ordinary sense. It doesn't have a hard boundary. It doesn't have an edge. What it has is a tiny nucleus where almost all the mass lives, surrounded by a region where electrons are likely to be found. Let's zoom in. At the center is the nucleus, protons and neutrons packed into an unbelievably tight space. If you took all the nuclei from all the atoms in your body and squeezed them together, you'd get something smaller than a grain of sand. That's how much stuff there actually is. Everything else is not stuff, not in the way you mean it. Now here's the scaling trick, and it's one of the best ways to feel how empty matter really is. Take a hydrogen atom, blow it up so the nucleus is the size of a marble, just a little glass marble sitting on a table. Where's the electron? Not circling a few centimeters away, not a meter away. It would be hundreds of meters away, a quarter mile, maybe more. And between the marble nucleus and where the electron cloud lives, nothing. Vacuum, emptiness. Now even that is still not accurate, because the electron is not a tiny ball flying around like a planet. That's the part most people miss. The electron is better described as a probability cloud, a fuzzy, smeared-out distribution. It's not at a point until you measure it. It's spread out. It's a region of likelihood. And crucially, that cloud is negatively charged. The nucleus is positive because protons are positive. So the atom is neutral overall, but it contains charge separated in space. Positive center, negative cloud. Now multiply this by every atom in your hand, every atom in the table, trillions upon trillions of nuclei, each wrapped in an electron cloud, and between those nuclei, enormous emptiness. So now the real question hits you in the face. If your hand is mostly empty space, and the table is mostly empty space, why doesn't your hand fall right through? Why doesn't your hand pass through the table like two swarms of gnats passing through each other? Why doesn't the emptiness in your hand slide through the emptiness in the wood? Here's where the magic happens. Those electron clouds, the outer regions of atoms, carry negative charge. And what happens when you bring negative charge close to negative charge? They repel. Not a little. They repel strongly, and the closer they get, the stronger the repulsion becomes. You felt this kind of thing with magnets. Push two north poles together. They don't meet. You feel that springy resistance. You can fight it, but the force grows as you push. That same style of resistance, force rising rapidly as distance shrinks, is exactly what you experience when you touch something. Your skin atoms approach the table atoms, their electron clouds approach, and the electromagnetic repulsion kicks in. It ramps up violently. You reach an equilibrium. The push from your muscles equals the push from the electromagnetic field. That equilibrium feels like contact, but there is no literal meeting of surfaces. Your hand is hovering over the table, supported by electromagnetic force. Let me give you a physical analogy that's imperfect but useful. Imagine two very powerful industrial fire hoses pointed at each other, water blasting out of both. The streams meet in the middle and churn into a turbulent barrier. Now try to push the hoses together. You feel resistance. Tremendous resistance. The closer you push, the greater the pressure. But did the metal ends touch? Not really. What you feel is the interaction, the force. Electron clouds behave similarly. As you push two objects together, you're pushing their charge distributions into closer proximity, and the field pushes back. Or use another analogy. Rub two balloons on a sweater and bring them close. They don't touch, they avoid, they repel. Now imagine that effect multiplied by trillions of atoms, all resisting simultaneously. That's solid. Now here's a subtle point that matters a lot. Most people picture atoms as little spheres with sharp edges. They imagine that if you push hard enough, the spheres will eventually meet and you'll get true contact. But atoms don't have sharp edges. Electron clouds fade out gradually. There is no crisp boundary where you can say, the atom ends here. It's like fog. Where does a fog bank end? You can't point to the exact last molecule of fog and say, after this it's empty. The density thins out gradually. Electron clouds are like that. So when you push one object toward another, the clouds begin to overlap slightly at their edges, and the repulsion increases dramatically. There is no final touch point because there is no surface to touch. So far you might say, okay, fine, so touch is really electromagnetic repulsion. That's already enough to explain a lot, but there's another layer, and it's one of the strangest and most beautiful rules in physics, the Pauli exclusion principle. Electrons are fermions, and fermions have a rule. No two identical fermions can occupy the same quantum state at the same time. Not because they're shy, not because they prefer distance, because the laws of physics forbid it. A quantum state is a package of properties: energy, location probability, spin. If two electrons had everything identical, they would be in the same state. And Pauli says, impossible. So when you push your hand against a table, you're not only bringing negative charge close to negative charge, you are also trying to force your electrons into regions already occupied by the table's electrons, and they refuse. What happens instead is that electrons are forced into higher energy states. They have to rearrange, they have to make room. That costs energy. It creates pressure. This pressure is not metaphorical. It's a real physical effect, degeneracy pressure. And here's the wild part. This is the same pressure that holds up a white dwarf star. When a star, like the sun, runs out of fuel, gravity tries to crush it. It collapses, and you'd think it could collapse forever, but it stops. Why? Because the electrons get packed so tightly that Pauli exclusion makes it impossible for them to all sit in low energy states. They must occupy higher and higher energies, and that creates a pressure that pushes outward. That pressure fights gravity. A white dwarf is literally held up by the fact that electrons refuse to share quantum states, and that same principle, scaled down enormously, contributes to the solidity you feel in everyday life. So when you press your hand on a table, you're fighting two things: electromagnetic repulsion, negative clouds resisting; quantum exclusion, electrons refusing to stack into identical states, two independent no's from nature. Now let's do a thought experiment. Let's shrink ourselves down to atomic scale, and let's watch a finger press against a table. At this scale, the first thing you notice is emptiness, vast emptiness. The nuclei are like distant specks. Most of the space is nothing. Around the nuclei, there's haze, electron clouds. Not solid shells, not walls, just probabilistic fog. Now the finger approaches, the table approaches, clouds drift near clouds, and suddenly you feel it, a growing resistance, not a collision, not a clunk, a pressure that rises as distance shrinks. The clouds distort slightly, they compress a little at the edges, but you cannot pass through. There is no moment where finger meets table. There is only a region where fields oppose motion, where forces balance, where movement stops because the pushback equals the push. From human scale, your brain calls that touch. From atomic scale, it's a stalemate. Now zoom back out. Every touch you've ever experienced was force. Your nerves detect deformation, pressure on your skin. They don't detect contact like two solids merging. They detect push. The sensation is real, but the mechanism is different from what your intuition suggests. When you hold a book, your fingers don't press into the book's atoms. Their electron clouds press against the book's electron clouds. You lift the book by electromagnetism. When you type, your fingers never meet the keys. They approach. The force rises, the key moves, the circuit closes, a letter appears. The whole everyday world is a choreography of electromagnetic interactions. Now you might ask, okay, then what about friction? If nothing touches, why do things scrape, grip, stick, slide? Friction is still electromagnetic. Surfaces look smooth, but at atomic scale they're jagged. Peaks and valleys. When two surfaces are pressed together, those irregularities interact. When you try to slide, electron clouds repel sideways as bumps try to pass bumps. That sideways resistance is friction. Even adhesion, glue, tape, bonding, works by electromagnetic attraction between molecules. The molecules settle into a lower energy configuration at a particular distance, not touching but held, and chemical bonds are like that too. Atoms in a molecule don't touch. They share electron density. They form stable arrangements. Forces balance at a certain separation. So you're not a bag of tiny balls stuck together. You're a dynamic structure of fields and probabilities and energy configurations. Now, at this point, some people get uncomfortable. If nothing touches, does that mean touch is fake? No. Touch is absolutely real because something real happens. Your skin deforms, your nerves fire, your brain receives information. You can distinguish rough from smooth, hard from soft, hot from cold. You get reliable data about the world, but you're sensing force, not contact. And in a deeper sense, force is the thing that matters. If two things could somehow touch with no forces, you wouldn't feel it. There would be no signal, no deformation, no information. What you call touch is the nervous system's interface for electromagnetic and quantum resistance. So the world isn't less real, it's just more subtle. And now we can say something honest about the deeper edge of this. At very small scales, the word touch starts to lose meaning. Electrons, as far as we can measure, behave like point particles, no size. So what would it even mean for 2 points to touch? Touching assumes surfaces, boundaries, extents. Quantum mechanics replaces that with interactions, probability amplitudes, exchanges of momentum and energy. The classical picture breaks down, so physics does something rare. It admits that the everyday word may not map cleanly onto the microscopic world. What exists cleanly are interactions. So let's bring this home. You have spent your entire life in a world of invisible fields. Every hug, every handshake, every time you leaned on a wall, every time you felt rain, every time you grabbed a doorknob, electromagnetism, across a gap that never closes. And that doesn't make it less meaningful. If anything, it makes it more impressive because it means connection doesn't require merging. It requires interaction. The universe is built out of particles and forces. Particles are what you call stuff. Forces are how that stuff relates. And the relating is what creates everything you experience. When you stand on the ground, you are not sitting on a solid slab of matter like a brick on a brick. You are being supported by electromagnetic repulsion. The planet is holding you up with fields. When you hug someone, your atoms don't mix, your surfaces don't merge, but your fields meet, your molecules respond. There is a pressure, a warmth, a transfer of energy and information. Nature doesn't let things touch in the naive sense, but it gives you something richer. A universe where everything influences everything else through laws that are consistent, predictable, and, when you really look, astonishingly elegant. So yes, you have never touched anything, and you never will. But you have interacted with everything you've ever held. You have been connected to the world through forces that are as real as anything in physics can be. Not contact, interaction, not touching, relating, and I think that's beautiful. Now here's the question, because it's worth asking. Knowing this, does the world feel less solid or more wondrous? Tell me what it does to your head.